So we just did a tannoy a minute ago, so I'm just going to give a couple of people, because this theatre is sometimes hard to find. But otherwise, we'll crack off pretty soon. But yeah, thank you all for coming. Who was here yesterday? Awesome. Did you know you were going to come back 2 days at that point? I went to do some Vox Pops with some of the families, and I'd be like, what time did you arrive? And they're like, yeah, 10 a.m. And that was like 4 or 5 o'clock. And is that? Yeah. So people arrive for like an hour and then stay for 6. Yeah. So, yeah, thank you for that. I hope you're enjoying it. This is only our 4th and our 3rd physical festival tomorrow. So I hope you enjoy it. We have got quite a range of shows and talks. And Brian Clegg, he literally said, do you want me to come back again? I was like, yeah, I do, because essentially I think he's awesome and has loads of amazing books. A lot of them are on my shelf. And as a local author, I just think it's kind of brilliant. So we're gonna kick off. But so fire escapes in the unlikely event. There was one in the presenters' hotels last night at 1 a.m. Are at the bottom here, and you can make your way out, through the main door, muster in the car park. Otherwise, really pleased to have our local celebrity author back in person at the festival tomorrow. Brian has been given several sellout lectures at the Royal Institution of London and has spoken at venues from Oxford and Cambridge universities to Cheltenham Science Festival. No one's heard of that. He has also contributed to radio and TV programmes, is a popular speaker in schools. Brian's a fellow of the Royal Society of Arts, a member of the Institute of Physics, was Royal Literary Fund at Bristol University, and is also editor of the successful popularscience.co.uk book review site. And according to my site, my count, which apparently is wrong, has written 97 books, but only about 40 of those are science. The rest don't count. So, but I think there must be at least 3 to go, because you can't stop until you get to 100, surely. So I will shut up now. Please welcome Brian Clegg.
Thank you very much. So this weekend, this event is all about science, and science is wonderful. That's why I love writing about it. But sometimes we get science a bit wrong. And when I say we, I mean those of us who aren't working scientists, which is most of us. And I just want to look at a few ways we do get it wrong, and misconceptions about science can get in the way of understanding what's happening. This comes out of a book that has 50 of these things in, but I'm just going to pick up on a few of them this morning. Sometimes it's about common sense. We all love a bit of common sense, but the fact is common sense doesn't always get it right. It does sometimes, to be fair, and some of the, if you like, folklore type of science, it has a basis in something. So I suppose the classic example is the old, red sky at night, shepherd's delight, red sky morning, shepherd's warning. The reality is, if there's red sky at night, well, we know that high pressure, which is kind of good, hopeful when it's coming in, for weather, traps particles in the atmosphere. It makes the scattered light from the sun as it's setting go out more into the atmosphere. So when you get red sky at night, what it's saying to you is probably the pressure is relatively high. And if high pressure is moving in at night, usually or often, that means there's going to be some good weather. So there's actual good basis on that. And similarly, if the high pressure is moving out in the morning, might be bad weather. So there's something to it there. Of course, the people saying this didn't realise why. It's not science in the sense that science is about understanding what's going on, finding out more about it, but it does kind of work. However, there are plenty of other examples where it doesn't. My favourite is Groundhog Day. I'm not talking about the movie. I'm talking about the thing in America featuring these little chaps. 2nd of February, which is Candlemas, was the day traditionally in Germany where badgers were used to predict the future. And it was carried over to America. They didn't have the badgers, so they transferred it to groundhogs. And the idea is basically they have a look at this groundhog on Groundhog Day. If it doesn't cast a shadow, then it doesn't get scared, apparently, and wanders around happily, and that means the weather's going to be fine. If it does cast a shadow, it ends up running back into its burrow, and for the next 6 weeks, the weather's supposed to be bad. And there's been plenty of studies. This incident is one of the most famous ones, Punxsutawney Phil. That's his day being announced. Plenty of study in this, and it has no reality at all. It just doesn't work at all. And I'm afraid that is true of quite a lot of folklore, science, as it were. So one way that science can be misinterpreted is when we're not really doing science at all, but it feels like it's a bit scientific. But another thing is that science itself, which is really about collecting and interpreting information, can need simplification to understand it. It's all very well, a scientist spends all their time working with it, they understand what's going on, but somebody has to simplify it, and that's another area where things can go wrong from the simplification. And some of the examples we'll be looking at in a moment involve going too simple, making it too simple. As I say, the book has 50 examples of these in. I'm going to cover just a handful of those and a couple of ones that aren't in the book today. But I'll start off with the one that the title of the book is Lightning Often Strikes Twice. And what that's reflecting is, of course, that old folklore thing, lightning never strikes twice. Now, lightning is a very impressive natural phenomenon and can do a lot of damage. A typical lightning bolt has same kind of power a mid-sized power station puts out in a second. So that's a huge amount of power in that lightning bolt. As it cuts through the air, it raises the temperature to higher than the temperature of the surface of the sun. That's why you get that flash of light, because it is actually heating the air up so much as it passes through. And they're quite common. Any time of year around the globe, there are maybe about 2,000 lightning storms happening. So they are really quite common, but the reality is, I don't know about you, but I've certainly never seen I've actually never seen lightning strike full stop, but I've certainly never seen it strike the ground, that is. I've never seen it strike, but I've certainly never seen it strike the same place twice. So it seems kind of natural thing. Oh yeah, it doesn't happen very often. And in fact, it was used historically as a way of preventing lightning strikes. And this is an example of how a misunderstanding, if you like, can result in bad science or pre-science. Because the people had never seen it happen twice, they used things called thunderstones, and these are thunderstones. And the idea was these stones have been struck by lightning, causing a hole in the stone. So what you do is get one of these stones, stick it up your chimney, and your chimney won't be struck by lightning because it's got that stone up it. Unfortunately, of course, these were actually Stone Age axes and hammers, not caused by lightning at all. So even if the theory had been correct, it wouldn't have worked. But in fact, of course, it isn't. It's become almost proverbial, this whole business of lightning never striking twice. When we use the expression, we're not normally talking about lightning, actually. And there's a lovely example in an old book from the 1860s where the main characters have just survived almost being hit by a cannonball. And one says to the other, "Never fear, Brom, sit down on it," that's the cannonball. "If you wish to be safe, lightning never strikes twice in the same place, nor cannonballs either, I presume." In reality, of course, how could a lightning bolt know not to strike twice? I mean, it's not like it's thinking, it's not, God up there, Zeus throwing lightning bolts, saying, "Oh, I've hit that place before, I better not throw it there again." The fact is, it can't know. And the Empire State Building, typical example of something that has plenty of lightning strikes, about 25 on average in a year. Sometimes a single storm, it's resulted in as many as 15 strikes. And for that matter, even individuals have been hit more than once. This guy is the world record holder. He was never killed by lightning, but he was hit 7 times by lightning. And the hat apparently demonstrates one of the strikes, so that burn on it was caused when he was hit on the head by a lightning strike. Not that I'd recommend going out and trying this. People do get killed by lightning, but the fact is, lightning certainly does strike more than once. I'm going to move on to a rather more modern kind of misconception, and I think it's quite interesting. The first one was from the book. This one I've called a Schrödinger problem, in that it both is in the book and it isn't in the book. So if you buy a copy of the book out there, it is in it, I suspect. But what happened after the book was published, and this is an example of another way science can be misinterpreted, the wife of a senior executive in the publisher said, "I don't like this because it says something I don't agree with really." And so they took it out, and it was replaced by a different item because the publisher's wife didn't like it. And the reason they didn't like it was because of emotion. that sometimes an emotional response, which we sensibly get to important things, can get in the way of interpreting science. And this particular topic is about plastic waste and climate change. And I was listening to a radio program, and the presenter on it said, "Oh, I'm reducing my plastic waste to help with climate change." I thought, hang on, there's something not quite right about this statement. So let's just look into those elements there that are in that statement. So climate change is something we want to do something about. It is real. It is, I would argue, the most important environmental issue that we face. We do need to do something about climate change. But even there, even in that statement, there's a problem potentially of oversimplification, because it sounds like climate change is bad. It sounds like greenhouse gases are bad. Climate change can be bad, but it sounds like greenhouse gases are bad. The things that cause climate change. That would be a sort of immediate reaction to that if we oversimplify. The fact is, actually, greenhouse gases are wonderful. If we did not have greenhouse gases in the atmosphere, the average temperature on Earth would be minus 18 degrees C. There would be no liquid water. There would be no life on Earth without greenhouse gases. The problem with greenhouse gases is not that they exist, but having too much of them is bad. So it's a little bit subtler than just saying greenhouse gases are bad. The other aspect of this, of the two things that this TV presenter, radio presenter brought together, is plastic waste. And again, the oversimplified version is plastics are bad. Now actually, plastics aren't bad. Plastic of itself is a wonder material. It has saved many lives. It enables us to keep food safe. It enables us to produce medical equipment. It's a good thing. What's wrong is the misuse of plastic. So things like microplastics getting into the water, waste in the sea, and all that kind of stuff. Yes, that's bad. But it's actually how we use it that's the problem. It's not that plastic is inherently bad. But the real problem here in the initial statement was linking plastic waste and climate change. They're both environmental issues, but this presenter assumed that just because they're environmental, they are both the same thing. The fact is, plastic waste has no significant impact on climate change, though interestingly, attempts to replace plastic actually are damaging as far as climate change goes. Some of them. And the reason for this is climate change is about greenhouse gases, as I say. If you lock carbon away in plastic, it stays in that plastic for hundreds of years. It does not get into the atmosphere, so it does not cause climate change. If you may replace it with something that's biodegradable, that biodegradable substance will give off greenhouse gases as it biodegrades. So it is marginally worse for climate change than is plastic. Now, I'm not saying that that means we mustn't use anything biodegradable. But what I'm saying is you've got to make a balance on your priorities. You've got to say, is climate change the most important environmental issue, in which case perhaps I shouldn't use biodegradable materials? Or do I want to balance between climate change and the physical environment, in which case perhaps I'll move away from plastic a bit? Or do I want to go totally mad and never touch a plastic thing in the future? It's up to you. But the fact is you have to weigh up those priorities. We oversimplify and we get it wrong. And I think the most important thing with environmental issues is to watch out for people who try to tell you something's environmentally good because it'll sell. Just be always wary of that. Watch out. Find out if it really is good for the environment. Now that one's a bit on the serious side, so let's go to something a little bit lighter. And we're back to folklore on the subject of lemmings. We like a good lemming, don't we? So, could somebody, just for my benefit, because I'm ignorant, tell me, what does it mean if you say somebody's going to behave like lemmings? Any suggestions as to what that means? They're going to fling themselves off a cliff. Absolutely. That's what those lemmings do. They're suicidal, thank you. Now, lemmings are rodents. They're real things. They live in the tundra. They're rather cute, actually. Look like a cross between a guinea pig and a rat or something. And as you say, they are supposed to be suicidal. Now, it's certainly true of lemmings that they undergo mass migration. So large numbers of lemmings move from one place to another. And when they do, the number of lemmings in the area decreases hugely. So people can think, oh, what's happened to the lemmings? They've suddenly disappeared. And it's also true that they can attempt to cross large bodies of water in their migration. And they have sometimes been observed probably trying to cross a sea, thinking it's a lake, and failed. And that seems to be the origin of the myth, the broad myth, that lemmings are a bit dodgy. I read a book recently written in 1922, and it does refer to lemmings attempting to cross the sea. So the idea was around as far back as that. But the first idea we had there, the leaping off the cliff, is surprisingly modern. And specifically, it comes from this bit of video. Those are lemmings, and they do appear to be leaping off the cliff. Okay. Now that video comes from a 1958 Disney film called White Wilderness. And I think what's quite interesting when you look at the poster for that is the bit up the top, exciting entertainment. Okay? This is not a David Attenborough documentary, and even those are faked a bit. This was entertainment. You'll find in it, if you watch it, the animals tend to be rather anthropomorphized. I can't say that. Something like that. They are basically given the kind of feelings and expressions that humans might have. So they think, "Ooh, this looks interesting," or whatever. The narration suggests that these lemmings have mistaken the sea for a lake, and that's fine. That's almost possibly scientific. The problem is this leaping off the cliff bit, the thing we all associate them with. As far as we can tell, that bit of film is the first time that has ever been seen. That had never been seen before. And I'm afraid, unfortunately, although there's not absolute proof, there is strong suggestion that they were assisted, that they didn't leap off the cliff, they was pushed. So lemmings, definitely folklore, mostly, frankly, not true. I'm going to move back just a tiny bit from 1958 to the birth of the universe, which is admittedly going back quite a long way. And the theoretical scientific statement I'm dealing with here is the Big Bang explains where the universe comes from. So anybody like to give me a sort of compact definition of what the Big Bang is? What are we talking about if we talk about the Big Bang? Yeah?
The Big Bang is an event that started the creation of the universe.
Okay, an event that started the creation of the universe. That's a great description of it. Thank you very much. It's probably, surely, the most famous theory in all of cosmology. That's the science of how the universe works, if you like. I mean, it's even got its own TV show, let's face it. This is a serious theory. And it was actually named by an English physicist called Fred Hoyle in a radio broadcast back in 1949. Now, Hoyle himself, with a couple of other scientists from Cambridge, had championed an alternative theory that they called steady state. So rather than the idea of the Big Bang, of the universe expanding out from almost nothing to its vast size that it is today, they suggested it is growing, but it's always been growing. It never had a beginning. It's just gone on forever, growing and growing and growing. And interestingly, this was actually inspired by a rather fun 1940s horror film, I'd recommend it, called Dead of Night, which starts with exactly the same scene as it ends. So if you watch it in a loop, as it were, it never stops. And this apparently, allegedly, gave them the idea of this steady state theory for the universe. Now, Hoyle, when he gave his radio broadcast, this is part of his script, said these theories, which are referring to the Big Bang, were based on the hypothesis that all matter in the universe was created in one Big Bang at a particular time in the remote past. And this was the first time that term Big Bang had been used. It's often been said that Hoyle was being nasty to his opponents because he didn't agree with the Big Bang theory. He wasn't. There just wasn't a nice compact term for it in the same way that there was for steady state. He was just being, giving it a useful label. And the Big Bang won of the two theories. It proved more like what was actually observed than steady state. Though it did have to be modified a bit to fit. The reason we can say that is that now we can see out further and further and further into the universe. We see further and further back in time because light takes time to get to us. And we can now see that the early universe was very different from the universe as it is now. And so the idea it's always been basically the same but getting bigger and bigger didn't apply. Now I ought to say that Hoyle did modify his theory too to fit the new data, just as actually the Big Bang theory had to be changed from its original form as new data came in. But unfortunately, it had always been sufficiently sidelined, it never came back. But the reality of the Big Bang theory is it doesn't actually do what it says on the tin, at least what it says on that tin, that it explains where the universe came from. And Hoyle actually pointed this out. What he basically said is, again in his talk, that what it does is puts the very beginning out of sight. It makes it impossible, if it's true, to ever know what happened right at the start, to ever know how the universe began. So it doesn't explain where the universe came from. It doesn't explain how it began. It doesn't explain where the natural laws come from. It's brilliant at explaining how you get from a very small universe to a very big one. What it doesn't do is explain that start, where Hoyle's theory did, because it said there isn't a start. It's just gone on forever, the way it is. So it's a very small detail, but it's another example of how the oversimplification, the idea that, yeah, the Big Bang explains everything about how the universe starts, it doesn't. It doesn't tell us anything about the universe starts. It tells us how it grows, how it came from almost nothing to something huge. It does not tell us how it started. Come back down to Earth from the Big Bang and think about how we see films, see something moving in a film. And the traditional explanation of this, which was considered science until quite recently, is something called persistence of vision. And it was actually dreamed up in Victorian times, probably a response to the work of somebody called Edward Muybridge, who's an English photographer who produced these quite famous sort of sequences of images of moving things, which he then strung together to produce the first ever projected moving pictures in this fashion. And the fact is, it's a series of still photographs, but you see something that seems to be moving. Why? How can that possibly happen? The explanation given was persistence of vision. And the idea of persistence of vision is basically that you see one of the still images, your brain hangs on to that long enough that by the time the next still image comes, you've still got the other one, so they merge together and you see movement. Now clearly, actually, if you think about it, this is nonsense. If you have a picture and you put another picture on top of it, you don't see movement, you see a mess. It all goes blurry and messy and horrible. It's not right. It's not what it's about. And it wasn't until relatively recently that it was understood actually how it does work. And in fact, you can still find persistence of vision as an explanation online if you look for it. What really happens is the brain is not a camera, or the brain-eye combination. It doesn't work like a video camera. What it does is gets information about shapes, colours, contrast, edges, how things fit together, how things move, and puts it together to make a fake picture. What you see of the world is not a moving picture. It's what your brain is assembling from all these bits of information. It makes it up as it goes along. And normally it works really well. But we do know it's faking it. For example, you have a blind spot. There's a bit in your eye that doesn't work because the optic nerve at the back that connects it to the brain, where that's connected, there are no sensors, as it were. It can't pick up any information there. You should have a black spot in the middle of your vision. You don't, because your brain fiddles it for you. It takes all the other bits of information it can, assembles it together, and gets rid of the black spot. Similarly, there are things called saccades. Your eyes do not actually look at something and stay fixed on that thing. They're always jerking about. Very quick, tiny movements. It's the quickest muscle movement in the body. They're zooming around all the time. If you actually saw what your eyes were seeing, the whole world would be jerking around all over the place all the time. But your brain doesn't care about that. It's just assembling bits of information and making up a picture. And that's exactly the same of how it makes moving pictures out of a series of stills. It's not really seeing moving pictures. It is making that up and putting it together. And I think the best way of seeing this in action is when we look at an optical illusion. Optical illusions demonstrate to us that the brain is doing something that isn't actually what you see. This is one of my favourite optical illusions. It looks a bit like a chessboard. And actually what we'll do is just take the lights down on this one because it's good to see this a bit more clearly. Chessboard, cylinder, shadow. Nice, simple stuff. Two squares on there, one labelled A, one labelled B. Both squares are exactly the same shade of grey. It's only your brain that knows what shadows are like, knows what chessboards are like, that is making it look that they're different colours. They're not different colours. I can't 100% prove it to you. I know it is, and I still see it. But what I will do, I'll just move A to B. Honestly, I'm literally just moving it. I'm not changing the colour of it in any way. They are the same shade of grey. Just pop that back and do it one more time. They're exactly the same shade of grey. I'm not changing the colour as it moves. So I think that's a good demonstration of the way your brain is fooling you when you see things. Now I'm going to move on to something a lot of us worry about these days, which is food labels. And it's another place where simplification, oversimplification, can get in the way of the science. So, just quick show of hands, how many people here, when you buy some food off the shelf, do you ever look at the label on the back that says what's in it? I do. Don't have to, it's not obligatory, but it's at least half of you do look at those food labels. So, anybody who did put their hand up, anybody care to volunteer why? Why do you do it?
Salt.
Sorry, just ask the young lady at the back.
My mum has lactose intolerance, so I look at the stuff and make sure that there's nothing that I don't like or smell.
So, to see if there's something you don't like in it, yeah? Any other reasons you look? Yeah.
Well, similarly, my wife's got allergies, so I don't want to be the person that poisons her.
Yeah, really important. If there's somebody in your family who's got allergies. Anything else? Has that covered it? Yeah.
Salt content. I don't want my family ingesting too much salt that's hidden in food.
Yep, so that's salt content. You don't want too much salt in your diet. Don't want your family having that. Yeah. Calories, absolutely. So there's lots of good stuff in there. And I'm in no way putting it down. But there's a couple of things about food labels you have to be really careful about, or that can be downright confusing or misleading. And to save myself some effort, I'm going to show you a little video now about one aspect of that, which is the strange percentages that you see on the back of food labels. If you take a look at the contents list on a packet, you can be surprised. I've got here a pork sausage and it tells me it's 151% pork. What can that possibly mean? Only game shows ever come up with percentages over 100. And this isn't just about sausages. You'll find all sorts of products where it's the case.
So, has someone got their sums wrong? Well, no, but it is a little confusing. In most cases, manufacturers don't have to list the percentages for any ingredients that aren't in the name or picture. They just have to list them in order of weight, starting with what makes up the most. So, in this honey nut wheat cereal, it's honey, nuts and wheat that need the percentages listing. But look carefully. Sugar, the second biggest ingredient after wheat, doesn't have its percentage listed.
If I take a look at my cereal packet, I'll find that the numbers aren't what I expect. It tells me I've got 84.2% wheat. It doesn't give me a number for sugar. Then I've got 10.6% nuts and 1.9% honey. By law, they're not required to tell me the exact percentage that's in there, but they do have to be in the right order. So I know that there has to be at least 10.6% sugar, and that gives me a total of 107.3%.
That high percentage isn't down to bad maths, but to what's called the mixing bowl rule, which states that the percentage of each ingredient shown needs to be based on its weight in its raw state before it's been cooked or treated. And that explains why the numbers on the label don't always stack up, because many ingredients reduce in weight when they're cooked, as Brian can show us by making some marmalade.
What I'm going to do is something very similar to the way that a manufacturer will weigh things first and then do the processing. What I'm going to do is start with 100 grams of sugar, and I'm going to put 300 grams of oranges in there and see what happens.
So, in our mixing bowl, the 100 grams of sugar is equivalent to 25% of the total ingredients. The 300 grams of oranges make up 75% of the total mix.
Okay, so let's get them on the stove, give them a bit of heat.
Products like cured meats and cereals and these oranges lose moisture in the manufacturing process, so the weight of the final product may be much less than the initial ingredients.
Okay, it's been about 10 minutes, so let's see what the oranges now weigh. Instead of 300 grams, we've got 169. So the amount of orange that's in there has pretty much halved.
But the figure used to calculate the percentages of oranges in the final product isn't what's there now. It's still the amount that was initially put into the mixing bowl. Still scratching your head? Don't worry, all you need to know is that thanks to all that cooking and the way the numbers are worked out for labelling, if our marmalade was being sold in a shop, the oranges would be listed as making up 112% of the final product. And Brian doesn't think that's right, because those changing numbers can distort the percentage of other ingredients you might be checking for on the label, like sugar.
We've now got, according to the way the manufacturers work it out, 37% sugar and 112% of orange, a total of 149%. What we really want to know is what the proportion of sugar is. And in the final result, there's actually over a third of it is sugar. But that doesn't come across when you use the manufacturer's figures. The manufacturers do this because the EU regulations allow them to. But really, there's no reason why they shouldn't tell us exactly what's in there now when we're going to eat it. So, one thing that's confusing about those things on the back can be those numbers. When you go home, just have a look at your cereals. I can almost guarantee you'll find a breakfast cereal that has those numbers that add up to over 100%. The other thing about them is more about the kind of things we mentioned earlier, which is, if you like, the scary bit. Now, one thing is some people watch out for is chemicals, like chemicals to be added to our food, and that's fine, but you do have to bear in mind that actually everything's made up of chemicals. So actually, some of the chemicals in there are perfectly ordinary, natural, and sensible. For that matter, quite a lot of people worry a little bit about E-numbers. Now, E-numbers is just a mechanism for labelling various additives, but they aren't all artificial and nasty. Anybody like to guess what E300 is, unless you're an E-number expert and know already? Or anybody? Suggestion? No? It's vitamin C. So I wouldn't worry too much about having a bit of E300 in something you're eating. Similarly, E164 is actually just saffron, the spice. So E-numbers of themselves aren't enough. And this is an example of the oversimplification. We need to know just a bit more. You need to ask a little bit more about what's going on. There are some things you definitely need to watch out for. We had the mention of salt earlier, things like trans fats, hydrogenated fats, which we know are not good for you, various additives that might be a bit dodgy. But it can be difficult. When you actually look at a list, this is a genuine list of stuff in something, there's so much there, it's quite difficult to pick it out. What is bad? What's not so good? What's fine? Is that legible? Yeah, it should be okay to read. Anybody spot anything there that looks a bit dodgy? Anything that you might think, not sure about that?
Aqua.
Because?
Who knows what it is?
Okay, aqua's water.
Yeah, but why is it not called water?
I don't know, but you find this always happening. I mean, it's in shampoos and things and all sorts of stuff, yeah?
I didn't know just about this.
Sorry?
Didn't know just about this.
Yeah, okay. One obvious thing to me is just look at the biggest things. If you add together the first two things, you've got water and sugar. So it's 94% sugar water, this thing. This product. There are one or two other things in there that are definitely dodgy. Phenylalanine's probably not great. Tryptophan, not sure about that. Oxalic acid, definitely a poison. That's the poison in rhubarb leaves, for instance. Butylated hydroxytoluene, methylparaben, not too sure about those. But do bear in mind, as you go down these lists, they get smaller and smaller amounts. By the time you get down to the bottom, they are absolutely tiny. And the thing about poisons is it's the amount that's the danger. Everything, pretty well every crop, every natural substance is poisonous to some degree. Luckily, it's a very low degree with most of the stuff we eat. But most stuff we eat does have poisons in it. So it's a matter of knowing what to look for is really important. And this, I think, illustrates it particularly well, because this is the contents list of something you don't usually see the contents list of. It's the contents list of a blueberry. I love blueberries, and they're probably the healthiest fruit there is. They're wonderful. But even so, we just don't know normally that it's in there. So just a little bit of knowledge, probably not great. We need just a little bit more. Find out a little bit more if you're going to look into this kind of thing. Okay, so that's fruit. I brewed these with my breakfast. What about you? So I thought it'd be quite nice to move on to this point, to toast. Now, there's an old saying, that toast falls butter side down. And it's certainly true that some observational laws like this are real. I mean, we're a bit back to the red sky at night. So, for instance, there's the whole thing that buses come in threes or come bunched up together. And that genuinely can happen. It's obvious when you think about it. If you've got two buses coming along, one stops at the bus stop, picks up, the other one is getting closer and closer to it. By the time this one gets to the bus stop, the other one's moved off, but there's nobody there because they've just been put up, so it gets even closer. They do tend to bunch up. That's a real thing. But some of the observational laws, things we say happen, are just about false memory. So we tend to remember the more dramatic things. We remember plane crashes more than all the thousands and hundreds of thousands of times planes take off and don't crash. We remember toast falling butter side down more than when it doesn't. I don't know. So to try this out, to sort this out, in 1991, the BBC did an experiment. Unfortunately, I don't have a video of this, but they allegedly demonstrated that toast does not fall butter side down. It was just 50-50, like the toss of a coin. Unfortunately, what they did was not let toast fall, they flipped it like a coin. Now, not surprisingly, if you flip a piece of toast like a coin, it does rotate, and at 50-50, it can come butter side down or not. The fact is, they didn't do it right. The subtle detail, if you like, wasn't quite there. In 2006, the Mythbusters TV programme did it again, and they actually found it was 58-42 in favour of falling butter side down because of the dynamic effect of the shape it gets when you butter it. Again, unfortunately, that's rubbish, because again, they were tossing it like a coin once they'd buttered it. The reality is, when you drop toast, you don't toss it like I don't know, you might, I don't know, but I certainly don't toss my toast like a coin. It typically falls from about waist height. It will typically slip off a plate, to come off the edge of a work surface, or you drop it off your hand. That's how toast falls. It's not flipped in the air. I actually experimented on this, as you see here. Genuine experiment, fell butter side down. It really does, genuinely does. Feel free to try it at home. Well, with parents' advice if you're a certain age. But no, it really does fall butter side down, because if it's falling from that height, as it starts to fall, it hasn't got time to rotate the extra turn. It's too low. It's not falling fast enough. It really does work. Now, the final thing, which is going to be probably the longest bit of what we're going to be talking about, starts with tossing coins. This is one that isn't in the book. And I want to look at basically at two things: the way that coin tosses even out, and I'll come back to what I mean in a moment, and how the complexity of people being involved in experiments affects the outcome of those experiments. And often these experiments involve randomness or probability, like the tossing of a coin. So let's start very simply. If I toss a coin, what's the chances I get a head? Anybody like to tell me? Yeah?
50%.
Yeah, 50%. So 50-50, heads or tails. Actually, when you toss the coin, there's very slight advantage to the side facing up. So something to watch out for when you do next toss a coin. But the reality is, it's pretty much 50-50. So imagine I toss coins, and actually I get, say, 5 heads and 2 tails. Now, that's not 50-50. So would you say over time that the tosses will even out? Let's just quick show of hands. How many people would say over time the tosses should even out, so you get roughly the same number of heads and tails? Does that make sense? Yeah, that's about half of you. Okay. We'll come back to that. So to think about that, imagine I've got a coin, I toss it, and I happen to get 5 heads in a row. I'm going to take another show of hands, so I'm going to ask you for 3 options. The first one will be, is it most likely the next throw will be a tail, because that will help it to even out? Is it most likely the next throw will be a head, because I'm on a lucky streak, a winning streak, or whatever you like to call it? Or is it equally likely that the next one will be a head and the next one will be a tail? So let's just start with the first one. How many think it's more likely, I've tossed 5 heads, it's more likely the next one is a tail than a head? Anybody? 1, 2, 3, 4. Okay, 4. How about it's more likely the next one will be, oh, sorry, I said a tail, didn't I? A head. I meant a tail. Beg your pardon. How likely is it more likely that the next one is a head? So it's the same again. Okay, nobody? And how many of you say it could be equal probability, so equally heads or tails? Yeah. And that makes absolute sense, because the fact is, I'm going to try this in a minute, but the fact is the coin has no memory. It's a bit like the lightning. It doesn't know what happened before. How can it possibly choose to be a tail to make things even out? It can't do that. It has no idea. So as a demonstration for this, I'm going to need an assistant for this. Yeah, if you put your hand up first, would you like to come down to the front? I'm going to toss a coin, and through huge amounts of effort prior to this time, I've got 9 heads in a row with this coin. So hopefully it's a 50-50 chance it's going to be a head or a tail. Or could it be a tail to even things out? Let's toss the coin nice and loud to see what it is.
Heads.
It's a head. I've got 10 heads. Shall we push it? Let's push our luck. Whoop.
Heads.
11 heads. Just out of interest, I'll turn the coin over. What do you see?
Heads.
Heads. Oh, thank you. Thank you very much. I think a round of applause for that assistance there. Thank you. It is a double-headed coin. It does always toss heads. And actually, some people say, with that question a little bit further up, the most sensible thing probably is to say it's more likely to be a head, not because it's a winning streak, but because somebody's probably more likely to be cheating than not. Because that's what people are like. Well, some people. I'm not you, of course. So, the reality is that coin tosses need never get closer to 50-50, no matter how many you do. So let's imagine you're sitting there, you're tossing a coin, you've got more heads than tails. And it can get closer and closer to 50-50, it will get closer and closer to 50-50, but you could always have tossed more heads than tails, because the fact is you might add, say, 1 extra head over the tails every 10th throw, and all the rest even out. It'll get further and further apart. It need never actually get closer to 50-50. That expectation it's going to is based on this thing that we have this idea. It ought to be fair, it ought to even out. But actually it doesn't work like that. Each toss is independent, each toss could result in either. And actually even scientists often forget that people are actually part of an experiment. Of course, that experiment we just did with the tossing a coin was cheating, but even if people aren't cheating, people are involved in experiments. And I think a great example of this is something called the ultimatum game. I'm going to need 2 volunteers for this one, and it may involve getting money. Okay, I think your hand went up first, and the gentleman there, if you could have the 2 of you down here. Okay. It's a very simple game that our 2 competitors are going to play. What I've got, I'm afraid it's not a lot of money. I've got £1, basically, which they could win. Okay? And I'm going to ask each of them a question, and it depends on how those questions are answered, whether or not they win some money. So what's your name? Natalie. Tilly, sorry. Tilly, I've got £1 that I'm going to give you. I'm going to ask you in a moment how it should be split between you. You can choose whatever you like. You can take the whole £1, you can split 50-50, you can have 90p, give 10p, whatever you like, it's up to you. Okay, so think about that for a moment. I'm going to tell you what the other question is before I ask you that. So, sorry, what's your name?
James.
James, okay. When you've decided and told us how you want to split the money, James can say yes, and if he says yes, you get the amounts of money in the split you say. So if you say, I get £1 and James gets nothing, that's what happens if he says yes. However, if James says no, neither of you gets anything. Okay? So he's got the power after you've made the decision of how it's split. That's why it's called the ultimatum game, because he has this kind of ultimatum, the ultimate decision. But you decide first how you want to split that pound between you. Okay? So how would you like to split the pound?
He gets 60, I get 40.
He gets 60, you get 40. Wow. James, would you accept that?
Yes.
Yes. Okay. Fair enough. There we go. 60 and 40. There's your 60.
Thank you.
There's your 40. Thank you very much. Can we give him a round of applause? Now, the ultimatum game is a favourite among psychologists, sociologists, and the like. It's been played many, 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 many times around the world. And generally speaking, if you think about what you would actually turn down if you were playing that game, the researchers say two things. One is pretty well everybody will accept 50%, so you could have got away with 50. And in practice, many will accept 30%. It varies slightly culturally from region to region. But certainly if you offer 50-50, on the whole, the other person will accept it. I have to say, you are the most generous person I've ever played this with. It normally is 50-50 that somebody will offer it in these circumstances when they're in front of an audience. And the other thing that researchers say is it's not dependent on the amount on offer. Now, I think that is an example of scientists themselves having a misconception about science, because scientists do experiments in certain ways. They don't do them in every possible way. And if you look at the papers that are on this kind of experiment, they usually give between £1 and £10 in that experiment. And that's fine. But let's say that Elon Musk came along, you just imagine him doing this, frankly, and provided £10 million for the ultimatum game. Okay? Just think about it. Realistically, if you were the second person, the person who said yes or no, would you say no if the first person said, I'll keep 9 million and I'll give you $1 million? Would you really say no, honestly? I doubt it. I frankly doubt it very much. The fact is, the experimenters doing this have not really thought about the whole picture. And what I'm going to do, actually, is a little experiment now with you. This is something I've been doing for a few years. Now, you have to do this very carefully because of the raked seating here. I'd like you all to stand up, please. Let's be very careful as you do this. We don't want any accidents. Okay. Now I'm going to say, remember, there's £10 million on offer. Oh, sorry, I ought to say, by the way, this money does not exist. So this is a hypothetical experiment, just to be absolutely sure. £10 million on offer. I'm only going to offer you £100,000 to start with. So that's just 1% of the original, far, far less than most people would normally accept, according to the scientists. And I'm going to bring that amount down from 100,000, chunk by chunk. When we get to the point where you would genuinely think you would turn it down, please sit down. So if you would turn down £100,000 out of the 10 million because the other person is being so horrible, and I'm keeping 99%, sit down now, I'll bring that number down. And when we get to the number you would genuinely turn down, as far as you're aware, sit down, please. So you could have, from the 10 million, so I said 100,000, 90,000, 80,000, 70,000, 60,000, 50,000, 40,000, 30,000, 20,000, 10,000, 5,000, 4,000, 3,000, 2,000, 1,000, 500, 400, 300, 200, 100, 50, 20, 10, 5, 1? Okay. Thank you very much. Okay. Now, there's a number of interesting observations from that. As I say, I've done this experiment many times with groups of people. Usually, roughly half the people have sat down in the region of 10,000 to 5,000 pounds. Now, I think, to be honest, it's one thing to do it hypothetically. It's another thing to have somebody holding out 5,000 pounds to you and say, no, I won't have it because that other person's getting so much. Yes, it is unfair. Yes, you do feel hard done by. But the fact is, you turned down £5,000 of free money simply to make a point. But, yes, sorry.
Have you ever done that the other way around? That guy keeps 900,000, that guy keeps 950,000?
No.
Because that's, in a sense, plays more to the unfairness of it.
Yes, yeah, that's true, but no. I kept it in this format because this is the standard format, basically how it's used worldwide. I think we exaggerate a bit. In fact, somebody did, I won't point them out, but somebody did sit down at 50,000. I think this is very unlikely, realistically, if it's real money. Several people had sat down by 20,000, and they're the ones, if there are any burglars in the audience, they're the houses to go around. They've obviously got money throwaway. But it does get really interesting. The percentage you get down to is a fraction of a percent, actually. And the experimenters, on the whole, have kind of forgot what real people are like when they're doing these experiments, because they do them in very controlled circumstances. So even they can oversimplify the science sometimes. Incidentally, I don't know what it is about Swindon, but normally nobody's still standing at £1. And we had quite a few. The first time I ever did this, I had somebody I knew in the audience, and he stayed up to £1. But I knew he was from Yorkshire, so it didn't surprise me. And the other thing was, that this genuinely happened. The person sitting now next to him actually gave him £1 to sit down, which I thought was wonderful. So if your neighbour didn't give you £1 and you were still standing up, they're tight. But no. The remarkable thing is, that any amount, in the end, is free money. Why on earth would you turn it down? But the fact is, human beings complicate things to an extent, as I say, that I think even the experimenters sometimes forget it. And the reality is, science is great, scientific experiments are wonderful, but the fact is, they sometimes don't reflect reality. For a long time, mice were used a lot as models in medicine, for instance. Mice are very different biologically to human beings, and it was realized fairly early on, they still are used, but that you need to go beyond mice because they are too different in terms of the outcomes. Similarly, many psychology, sociology type experiments are done using students, university students, because A, they're cheap, and B, they're handy. You don't have to go somewhere to get them. But university students are not representative of the population as large. So, you do have, even scientists can get this wrong. You do have to think a little bit beyond how you apply it. So just to pull it all together, it's easy to have misconceptions about what's happening. It could be common sense going a bit wrong. It could be just misunderstanding. Or it could be that we're just making things a bit too simple. When I quite often have been gone to a radio studio when there's some scientific breakthrough kind of thing. I remember a while ago, there was an experiment that looked like it was sending particles called neutrinos faster than light, and everybody got really excited about it. And frankly, the answer was, well, actually, it's probably not going to be right. And it wasn't. It was actually an error in the way it was connected. The fact is, it's usually a bit more complicated than it just looks at first sight. I think it's really important, we heard this a lot during COVID, follow the science. It is really important, but you really have to be careful where the science is pointing. It's not, sometimes it's absolutely clear. It's very simple, very straightforward. The science of gravity, the fact that if I get a book and let go of it, it's going to hit the ground. I don't think that's anything but straightforward. I don't think we have to worry about that too much. But sometimes it isn't always obvious the way that it's pointing. I do have to say that one thing I do feel is TV science particularly can oversimplify. They're so enthusiastic about having pictures of Brian Cox standing on top of a mountain or whatever, they sometimes don't have time to do the science. Brian Cox writes great books, science books, with a colleague of his that have lots of detail, but the type of TV programs he does, there's very little actual science in it. And so, admittedly, with a tiniest bit of bias, I'd suggest the best solution is to read more. Because in a book, you can get a lot more depth. Doesn't mean it's going to be more complicated necessarily, but you can get more stuff into it. You can get a better understanding of it. You don't have to oversimplify to the same extent. So that's all I was going to cover today. We've got hopefully a little time, a few minutes for questions. Afterwards, I'm going to be out by Bert's Books out there. If anybody wants to buy a book, I'm happy to sign it. But if you don't get a chance to ask a question, do come and ask me out there. either if you don't want to say it in front of everybody else or if there isn't time or whatever. I promise I won't force you to buy a book. Okay, so any questions? It's going to be really easy, right? Here at all. Yep.
How does the Monty Hall problem work?
Okay, so the question was, how does the Monty Hall problem work? The Monty Hall problem, basically, it's named after a game show in America that was hosted by somebody called Monty Hall. And the game show ends with 3 doors. And behind 2 of the doors is something fairly worthless. It's often portrayed as being a goat. And behind the third door is something really valuable, say a Ferrari or something like that. And what happens is the person who's playing the game has to decide which of the 3 doors they want to open. So they say, so the A, B, and C, I'll open door A. And what Monty Hall does is open a door and shows you what's behind it. So say he opens door C and shows you it's a goat. So now there are 2 doors left that haven't been opened. One's a goat, one's a car. And the question behind Monty Hall is basically, should the person who's playing the game stick with the door they first opened? Should they move to the other door? Or does it not matter? Because there's basically 2 doors, one with the car, one with the goat. Does it not, is it just 50-50 chance? It doesn't matter which you choose. In fact, just out of interest, so remember the 3 things you could do. You either stick with the door you've got, you move to the other door, or it doesn't matter which you do because they both have exactly the same chance. There's 1 car, there's 1 goat. So who thinks it better to stick with the door you've got? Okay, so 1, 2, 3, 4, 5, 6. About 10-ish, yeah. Okay, how many thinks it's better to move to the other door? Oh, considerably more. Okay. And how many thinks it doesn't matter which door you open because there's a 50-50 chance there's goat, there's car. That's quite... Okay. Now, I can only assume, possibly, that some of you have heard of the Monty Hall problem, because actually they were right when they said move. The ones who said move were right. You're actually twice as likely to win if you change your choice than if you stick with the one you first had. And when this problem first came out, it absolutely baffled people. But you can simulate it with a computer and things, and it really does work. You're twice as likely to win if you move than if you don't. Now, there's various ways of explaining it. I don't want to spend too much time in it, but one way of thinking about it is you've got 2 doors with a goat, 1 with a car. And what Monty Hall does is shows you which door not to choose. So he's actually shown you where one of the goats is. He will never open the door on a car. He knows what's where. So he has actually, there's 1 in 3 chance you're right. He'll show you which one not to pick. You ought to move to the other one because there's only 1 car with a door, but there's 2 with goats. Now, if that still doesn't make sense, I can only recommend, I've got a book called Dice World, which goes into it in a lot more detail. Unfortunately, I don't have it out there. But genuinely, I have simulated it on the computer. It genuinely does work. You're twice as likely to win if you move. Sorry, that was a very long-winded answer, but it's a nice question. Thank you. Any more questions? We're totally bamboozled by Monty Hall. Okay, well, thank you very much for coming. As I said, did we have any online? No? Okay. We're popping out now, as I say, 2 Bert's books. Please do come and say hello if you wish, and if you want to ask anything out there. But thank you very much for your time. I hope you enjoyed it.